relativity. So I will explore how reference frames affect the observation and description of motion and apply this understanding to analyze real-world context in fields like physics, engineering, and navigation, where perspectives on motion are essential. Okay, so Einstein, right? I mean, we associate relativity with Einstein. It's not just Einstein, but Einstein did realize that space and time together constitute a set of coordinates, right? Um, Almost all motion can be described in some sort of space during a specific time period. Okay. Basically, it works the same way that a 2D graph uses the pairs of coordinates. Like instead of saying the y direction versus time, you know, it's now space versus time. Okay. Space time is a model that fuses the 3 dimensions of space and the 1 dimension of time where events take place. Okay, so if you look at the picture, right, and you think of the ball that's inside of, this is the space. At this moment of time, we can say what the position is in space at that time. Okay, that is an event. So an event is one set of space-time coordinates that identifies a particular position in space-time. Okay? But the big idea behind relativity is the fact that the perspective from which an event is observed affects the measurements of space and time. Okay? Now, it affects the measurements, which also leads to different experiences of motion, distance, and duration, time, depending on the observer's frame of reference. Okay, so if we look at our picture here, you've got Mr. Yellow here, and he's like, wait, hold still, because the box is moving, right? But from Miss Red's perspective, she isn't moving, right? He is. Okay. So a reference frame is a way of representing the position and motion of a particle in space. Until now, we've always viewed events in the frame of reference of a spectator, kind of like Mr. Yellow, okay, watching from the outside. We call this the ground reference, okay? How does the event change when viewed from a different frame of reference? Okay, so let's put ourselves in the perspective of the object being observed, right? So Mr. Yellow is Mr. Yellow is observing Miss White or Miss Red. Let's put ourselves in Miss Red's shoes and look at it from her perspective. Okay. So, in Mr. Yellow's frame of reference, he's standing still. Okay. And then Miss Red is moving to the right along with the cart. Okay. So, to him, Miss Red is moving. But if you're in Miss Red's frame of reference, she's standing still, and Mr. Yellow is moving to the left as the cart moves to the right. Okay. So, for a frame of reference in which the laws of inertia hold, right? Remember, the law of inertia is, you know, an object at rest stays at rest, or in motion stays in motion, unless an external force acts upon it, right? So an inertial frame of reference is a frame that is not accelerating, right? So if you look at that, it says that it's If it's at rest or if it's moving at a constant speed, right? Constant speed, no acceleration. Not moving, no acceleration. Okay? So therefore, all inertial frames are moving at a constant velocity with respect to each other. Okay? So both frames could be moving. Okay? So to sum it up, we have space-time is a model that fuses the 3 dimensions of space and the 1 dimension of time where events take place. An event is one set of space-time coordinates that identifies a particular position in space-time. A reference frame is a way of representing the position and motion of a particle in space. An inertial frame of reference is a frame that is not accelerating.